Genetic algorithms parameter tuning is an essential aspect of mastering genetic algorithms, GAs, which are powerful optimization techniques inspired by natural selection. These algorithms rely heavily on parameters that govern their behavior, influencing both performance and convergence speed. Optimizing these parameters can transform a GA from a basic tool into a highly effective solver for complex problems across various domains such as engineering design, financial modeling, and machine learning hyperparameter optimization. The core principles behind genetic algorithm parameters. A thorough understanding of GA fundamentals provides clarity when adjusting its core parameters. At their essence, GAs simulate evolutionary processes through mechanisms like reproduction, mutation, and crossover. Reproduction determines how new generations are formed based on fitness scores, while crossover combines traits between individuals to explore solution space effectively. Mutation introduces random variations, preventing premature convergence but also risking divergence from optimal solutions. Balancing these forces requires careful parameter selection. Fitness function evaluates individual quality, must align precisely with problem objectives. Precision requirements dictate necessary solution accuracy levels in numerical optimization scenarios. Evaluating fitness functions for optimal performance. An improperly defined fitness function can severely limit GA effectiveness regardless of other settings. It acts as the primary feedback mechanism guiding evolution toward desired outcomes. The best fitness functions balance mathematical rigor with practical feasibility. They should be computationally efficient yet expressive enough to capture key characteristics of target solutions. In multi-objective optimization tasks, weighted combinations help maintain diversity among competing goals without overwhelming the search process. Note: avoid using non-smooth or discontinuous functions unless specifically required by application domain constraints. Crossbreeding strategies and crossover rate optimization. Crossover rate significantly impacts population diversity maintenance versus exploitation efficiency trade-off. Higher rates promote exploration at expense of local refinement opportunities. Selecting appropriate crossover operators depends largely upon representation format. Binary strings respond differently than real-valued vectors or permutation-based structures. Single-point crossover works well for simple string representations, whereas uniform crossover offers better mixing properties for complex feature spaces. Tuning crossover probabilities involves balancing exploration needs against computational cost implications associated with increased offspring generation complexity. Managing mutation rates for effective exploration. Mutation serves dual purposes within GAs, preserving genetic diversity and escaping local optima traps. However, excessive mutation disrupts promising solutions prematurely. Typical mutation rates range between 0.01% to 1%, depending on problem dimensionality and representation type. Real-valued parameters often require lower mutation magnitudes compared to discrete variables. Adaptive mutation strategies dynamically adjust intensities based on population homogeneity metrics measured periodically during execution cycles. Caution: never set mutation probability above 10% without explicit justification related to problem-specific requirements. Population size considerations in genetic algorithms. Determining ideal population size balances resource consumption against solution quality potential. Smaller populations execute faster but risk suboptimal results due to limited diversity. Larger populations provide broader sampling capabilities but increase memory usage and processing time requirements proportionally. The sweet spot varies widely depending on specific applications. Benchmarks suggest starting sizes around 50 to 100 for moderate difficulty problems, scaling up for high-dimensional. Optimization challenges requiring extensive coverage. Tip: monitor convergence trends early in runs to detect signs of insufficient diversity before wasting resources on unproductive executions. Elitism implementation techniques. Elitism ensures preservation of top-performing individuals across generations, accelerating overall progress towards better solutions. Implementing it correctly avoids stagnation risks inherent in pure roulette wheel selection methods. Varying elitism percentages according to problem difficulty helps maintain momentum without over-relying on past successes. Common values range from 1% to 10% of total population size. Combining elitism with tournament selection creates robust hybrid approaches capable of handling diverse landscape features present in many real-world optimization scenarios. Tournament selection mechanics and its impact. Tournament selection enhances GA stability by reducing variance effects seen in simpler proportional selection schemes. This method selects winners through competitive mini-contests rather than direct score comparisons. Tournament size determines competition intensity. Larger tournaments favor stronger candidates but may reduce exploratory capability too much. Typical sizes range from 2 to 7 participants per contest. Advantage: maintains good diversity levels even in later stages of evolution where most individuals cluster near optimum regions. Disadvantages include slightly higher computational overhead due to repeated comparison operations conducted throughout each generation cycle. Convergence criteria determination establishing stopping conditions prevents unnecessary computation while ensuring sufficient solution refinement occurs. Multiple criteria typically work together synergistically. Main indicators include reaching predefined iteration limits, achieving stable fitness plateaus, or meeting precision thresholds specified up front. Some implementations combine several measures simultaneously. For noisy environments, incorporating confidence intervals improves reliability assessments regarding whether improvements have ceased being statistically significant. Best practice: always allow some buffer period beyond initial estimates since unexpected discoveries sometimes emerge late in lengthy runs. Hybridization opportunities within GAs demonstrate remarkable adaptability when combined with complementary optimization methods creating hybrid systems. Such integrations leverage strengths from different paradigms working collaboratively. Common hybrids involve pairing GAs with simulated annealing for enhanced escape abilities or integrating particle swarm optimization elements to accelerate convergence phases. These combinations often produce superior results compared to standalone approaches, especially when dealing with multimodal objective landscapes containing numerous local minima/maxima. Implementation considerations include determining when and how frequently to switch between methodologies during execution cycles. Case studies demonstrating successful parameter tuning. Real-world examples highlight how meticulous GA configuration leads to substantial performance gains across varied industries. One notable success involved optimizing turbine blade designs using carefully tuned mutation rates. In pharmaceutical research, properly calibrated selection pressures enabled discovery of novel drug compounds with previously undetectable molecular properties suitable for treating resistant infections. Financial institutions applied optimized GAs to portfolio management, resulting in portfolios outperforming traditional models by double digits annually despite market volatility fluctuations. Lesson learned: domain knowledge plays a crucial role in identifying which parameters merit special attention during fine-tuning phases. Automated hyperparameter optimization methods. Recent advances enable automated tuning of GA configurations through meta-learning frameworks that analyze historical data patterns to predict optimal setting ranges. Bayesian optimization has shown particular promise in efficiently navigating vast parameter spaces, characteristic of modern GA implementations involving hundreds of adjustable factors. These intelligent systems continuously refine recommendations based on newly acquired performance metrics collected during successive trials, enhancing overall system responsiveness. Warning: automation doesn't eliminate need for human oversight entirely. Critical judgment remains vital when interpreting results from black box optimization engines. Performance metrics evaluation frameworks. Accurate assessment relies on well-defined evaluation protocols measuring multiple dimensions including solution quality, runtime efficiency, and scalability characteristics. Standard benchmarks track mean square error deviation rates, comparing generated outputs against known ground truth values, establishing baseline performance expectations. Comparative studies often employ statistical significance tests confirming differences aren't attributable solely to chance occurrences, improving validity of conclusions drawn. Consistency checks verify reproducibility of results under identical experimental setups, reinforcing credibility of reported findings. Computational complexity analysis, understanding theoretical bounds, assists practitioners in anticipating resource demands prior to initiating GA experiments. Time complexity primarily depends on three interacting components. Each generation requires O(n) operations for selection steps followed by O(n) log n sorting procedures typical in ranking-based approaches implementing elitism principles. Crossover and mutation contribute additional costs linearly proportional to population size, making them critical areas for optimization efforts aiming to minimize wall clock time spent waiting for completion. Observation. Parallel computing architectures offer considerable relief, mitigating some of these limitations, enabling faster resolution of complex problems previously deemed impractical. Future directions and emerging trends. Ongoing research explores innovative ways to enhance GA efficacy through unconventional approaches addressing current limitations faced by conventional implementations. Quantum-inspired variants show exciting possibilities, leveraging probabilistic states, allowing simultaneous examination of multiple candidate solutions, potentially revolutionizing combinatorial optimization fields. Integration with neural networks enables creation of self-adaptive systems, automatically modifying parameter values, dynamically responding to changing environmental conditions experienced during execution periods. Researchers continue investigating hybrid models combining evolutionary computation with reinforcement learning, seeking breakthroughs applicable to autonomous decision-making systems operating under uncertainty. Practical implementation guidelines. Successful deployment hinges on following established best practices, ensuring consistency across development, testing, and production environments. Version control becomes paramount when managing evolving codebases. Implement modular architecture, separating concerns cleanly, isolating fitness calculation logic from evolutionary mechanics, facilitating easier updates and debugging sessions as projects scale upward. Employ profiling tools, regularly monitoring CPU utilization patterns, detecting bottlenecks early, allowing timely interventions before they escalate into serious issues affecting project timelines. Recommendation. Document every change made during iterative improvement cycles, maintaining audit trails helpful for troubleshooting future complications. Conclusion. This discussion illuminated the intricate relationship between parameter choices and GA effectiveness, highlighting why thoughtful configuration constitutes a fundamental step toward successful implementation. By systematically evaluating all relevant aspects, from foundational theory to advanced customization options, developers gain comprehensive toolkit empowering them tackle increasingly sophisticated optimization challenges arising daily in technological advancement landscape.